Hello and welcome. In this video, I'll be covering section 2.5, which is over the chain rule. My goal for you by the end of the video is to be able to find derivatives using the chain rule, to be able to find derivatives using the general power rule, to be able to write derivatives in simplified form, and to be able to use the differentiation rules to differentiate algebraic functions. So what is the chain rule? So the chain rule, as you can see here, requires us to have some function of u that then has u being defined as some other function of x, and so that way when I combine them, notice it would turn into this composition f of g of x, and as long as the g of x is a differentiable function of x, then f of g of x would also be a differentiable function of x. So as you can see here in the middle, we have dy over dx would equal dy over du times then du over dx, which is probably a little confusing to start. So a different way that you can think of it is if you have this function written out the way it is, f of g of x, notice it starts with f prime of g of x, so we would just take the derivative of only the f function and leave g of x as the part that's been plugged in, and then multiply that by the g prime of x, or the derivative of that inside function. So I'll try and sum this up for you. So with chain rule, notice what this concept is doing is we're taking a derivative of a composite function, meaning that there's a function that's been plugged into yet another function. So in these cases, one of the better ways to think of it as an inside and outside situation. So you identify what function is inside as well as what function is outside, or you can also think of it like levels. So when we take the derivative of these things, as you can see from the formula on the previous slide, is we take the derivative of the outside function first and just leave the inside completely unchanged, and then we would multiply whatever that result is by the derivative of the inside part. So chain rule also will always have essentially a product when it's all said and done. Now, since there are potentially multiple ways to decompose functions, in other words, there could be potentially multiple options of how a function was maybe plugged into another function, we sometimes just have to try out a few options before we truly actually find the one that's correct or is easiest for us when it comes to doing the chain rule. Alright, so let's go ahead and practice a few examples of how we can decompose a function into two other functions. So for this, I'm going to go ahead and just use the names f and g, and I'm going to have this be like the composition where it would be f of g of x, which then means that the g function must be what I'm calling the inside, which then means the f function must be what we would call the outside. So for this first example, there's a couple of different options that we could go with, but I'll just go with which one makes the most sense to me. So the g function is usually easier to identify, so in this case I would just look for a function that appears as though it's inside of something else. So with this, x plus 1 looks like it's inside of a radical, so that would be my first instinct for the g, which then would leave the f of x function to have to be 1 over the square root of x. Now another option we could have done with this one was actually put the square root on the x plus 1. So if I did that really quick just to show what that would have looked like, we could have said that the g function was the actual square root, and then that means the f function must just be the 1 over x. For this one, I'm just going to go back to my first instinct of having the x plus 1 be my g function, and then the f be the 1 over the square root of x, which I remember if we needed to do like a derivative of, I would want to rewrite that using a negative exponent as well as a rational exponent to get rid of the radical. If I move on to letter B, again set up my two functions here. To me, if it's the inside function that I want to start with, I would just look for anything that looks like it's inside of something else. So for this one, 2x squared plus 1 looks like it's inside of a parenthesis, so that seems logical to me. which then means the f function must have been just x to the 5th power. Try the next one. If I look at what we have here, the function that looks like it's inside of something else, in this case would be like the rational function inside, so x squared plus 1 over x squared minus 1, which then means that the f function must have just been x cubed. And one more for good measure. The inside function to me looks like it would be the x cubed plus 3, or sorry, x cubed plus 8, which then would leave the other function, or the outside function, to must just be the cube root of x, which again, if I needed to do a derivative of that part, I would want to call that like x to the 1/3 power. So notice with each one of those were not the only options that I could have done for decomposing. Those were just the ones that at first glance seemed to stick out to me. So I always just look to see, are there any things, or any parts rather, that are either inside of a grouping symbol, such as like a parenthesis or even like a radical, and then I just try and say that would be my inside function, and then I kind of picture like, what if I just replace that with just the x, that must be my outside function. So notice with this slide here, what we're going to do is we're actually going to do the exact same functions as the previous one, so we've already decomposed them, but we're actually going to now truly find the derivative, so we'll actually apply the chain rule. So again, with this first one, letter A, we said that the f function was that 1 over the square root of x, which again we could write as x to the negative 1/2 power. And then the g function we said was the x plus 1. So when it comes to doing y prime for this one, I would do the derivative of the f function. So since that's x to the negative 1/2, I would just move the negative 1/2 power out front, keep the base the same, which in this case should be the g function, so x plus 1, and then it would be raised to a power of negative 3/2, because I would drop that power by 1. However, I'm not done with chain rule, because I have to do the times the derivative of the inside function. Well, the inside function was the x plus 1. Its derivative would just be 1. And so everything from here is now just going to be, how can I rewrite this, or how can I maybe simplify it? Looks to me like the only thing that would stay in the numerator would be a negative 1. So I'll just go ahead and keep the negative out front and just have 1 on top. And then that x plus 1 would go to the bottom to make that turn into a positive 3/2 power. And that would be my y prime function. So I'll go ahead and label it over here. If we go ahead and try the next one, hopefully you can kind of see that the outside function is this power of 5. So if I go to y prime, that 5 would just want to move out front. Again, just doing kind of that power rule idea. The base is still going to be the g function, which is the 2x squared plus 1. And then my power would drop down by 1, so drops down to a 4. But again, I'm not done. I have to multiply by the derivative of the inside function. So now I'm looking at the inside part. Derivative of that looks like it would turn into 4x plus 0, so just 4x. So if I wanted to maybe simplify that just a little bit, looks like I could multiply the 5 and the 4x and just call that 20x out front, and then leave that 2x squared plus 1 raised to a power of 4 in that parenthesis there. No need in expanding out that power of 4, because this technically would be the smallest or easiest version to actually plug into. Moving on to letter C, or example C here, I would go ahead and again notice that the power that's outside is this 3. So I'd start with that. So this y prime then is going to have the 3 come out front. My base of x squared plus 1 over x squared minus 1 would stay the same, but then the power would drop down by 1, so that now is going to have a power of 2 on it. And then that's going to multiply by the derivative of the inside. So the derivative of that inside function, now I'd have to use that quotient rule. So that would be low d high, so that would be x squared minus 1 times the derivative of the top, so that's 2x, minus high d low, so that would be the top x squared plus 1 times the derivative of the bottom, which also happens to be 2x. Then it's all over the bottom squared. So notice this one got a little bit more intense because the inside function was now a quotient and not just a single polynomial like the first two examples. So now at this point I would look to see if there's any way that I can simplify this for myself. So if we look at what we have, we've got this 3 parenthesis x squared plus 1 over x squared minus 1, all of that being squared still. And then see if we can simplify this. So I'd have, if I distribute that 2x through, I'd have 2x cubed. I'll go ahead and get a different color here so it differentiates a little bit. So I'd have 2x cubed minus 2x. And this other one, I'm going to combine the negative that's in front with that 2x. So distribute a negative 2x through. That would give me a negative 2x cubed and a negative 2x. So it looks to me like the 2x cubes are going to cancel out, and then the negative 2x and negative 2x, I could combine that and call it negative 4x. Then all over x squared minus 1 quantity squared. So it looks to me like I should be able to actually multiply out my numerators at this point. So y prime is going to equal, I've got a 3 times a negative 4x, so a negative 12x. That's also multiplying with an x squared plus 1 that's being squared. On the bottom, I have this x minus 1 being squared that's multiplying with another x minus 1 being squared. So I really could call that x squared minus 1 to now a 4th power. In other words, I can add those two exponents because those bases technically were the same of x squared minus 1. So that would be my final, most simplified version of that particular derivative. We'll do our last example here, example D. Again, we have the ability to rewrite this, so I'll just off to the side say this really would be the same as doing x cubed plus 8 to a 1/3 power. So I'd start with that exponent first. So y prime, once I start doing the derivative process here, it's going to be y prime equals, the 1/3 would come out front. My base of x cubed plus 8 stays the base, but my power drops by 1, so 1/3 take away 1, that would be negative 2/3. And then times the derivative of the inside function, which in this case is that x cubed plus 8, well, the derivative of that would turn into 3x squared, plus 0 technically. So now if I look at what I have, looks like the 3 should be able to cancel with the other 3 that's on top. So this would now be only, it looks like, x squared in the numerator. And then the bottom, I would be able to say it's that x cubed plus 8, then being raised to that 2/3 power. So again, I'm just dealing with the negative exponent by dropping it to the bottom, and anything that didn't have a negative exponent, I kept on top. So that's where the x squared came from on top, and the x cubed plus 8 to the 2/3 is on the bottom. So as you can potentially see from the previous examples there, is that there's somewhat of a shortcut to this chain rule that we can actually call a general power rule. So if you ever have something that's in this format of it's a full-on function being raised to a specific power, we actually can kind of shorthand it into that power would come out front. So notice the n comes out front. The function itself stays the same, but then the power on that function drops down by 1, so like it has done in all of the previous examples. But then I need to multiply by the derivative of that inside function. So notice that's where the du over dx would come from. So some books on occasion will actually simplify that a little bit and just make it this format of d over dx of u to a power of n will just turn into n times u to a power of n take away 1, but then times u prime to represent the derivative of whatever that u was. So let's go ahead and work through a couple more examples here. First one here being find the tangent line. So that means to come up with a line, I'm going to need to know what is the slope as well as what is the point. So So in this case, it says specifically when x equals 2, so I know the x-coordinate of the point is going to be 2. To get the y, remember, I would just plug it into the function itself. So for this one, if I just plugged 2 in, let's at least get the point taken care of. So then we can focus on the derivative part next. So that would be 2 squared plus 4, and then that whole thing being squared, but then cube rooted. So 2 squared is 4, plus 4 is 8. 8 squared would be 64. So I need the cube root of 64, which would actually turn back into 4. So the cube root of 64, because 4 cubed is 64, I know it would equal 4. So my point here is going to be 2, 4. Now I just need the slope. So remember, slope will always come from finding a derivative. So that means I need to figure out what y prime is. In this case, I might want to rewrite this. So instead of jumping straight to that, let's actually just rewrite the y using exponents here. So this really would be the same as doing x squared plus 4. And then that being squared but then cube rooted would really be the same as doing a 2/3 power. So remember, the power inside will always go in the numerator, and then the index of your root will always go in the denominator of your rational exponent. So now that I have y rewritten in a little bit easier format to actually perform the chain rule, again, the general power rule, which is the shortcut for our chain rule, is going to be the power comes out front, so 2/3 times my function that's inside remains unchanged, so x squared plus 4. But now the power outside drops by 1, so that would turn into a negative 1/3. And then multiplied by the derivative of that inside function. In this case, that would become 2x, because the derivative of x squared plus 4 is 2x. So now if I look at what I have and maybe try simplifying, doesn't look like anything cancels like the previous examples, but I can do the 2 times the 2x for the numerator, which would be just 4x. And then all of that over, I still have the 3 from the fraction in front, and then this negative exponent, I'll drop that whole term to the bottom. So x squared plus 4, all raised to a 1/3 power. So at this point, to get my slope, I just need to plug in that value of 2 for x, so y prime at 2 is going to be equivalent to 4 times 2 on top over a 3 times, and then I've got 2 squared plus 4, and then the cube root, or the 1/3 power. So altogether this is going to turn into 8 over 3 times, and then 2 squared is 4, 4 plus 4 is 8. Cube root of 8, though, is 2. So if that's 8/6, that should be able to reduce to really 4/3. And now I can use point slope form to come up with the equation of the tangent line. So my tangent line is going to be equivalent to, or is going to come from, doing y take away y1, so that was the 4 that we solved for at the very beginning, equaling the slope 4/3 times x minus the x1, which is the 2. So it looks like my only 2 steps that I would need to do would be to add the 4 to both sides, but also distribute that 4/3 through before I do that. So if I go ahead and simplify what those would turn into, I'd end up with y equaling 4/3 times x, and then 4/3 times a negative 2 would be negative 8/3. So if I have negative 8/3 that I need to add with 4, I probably need a common denominator, so I'd have to multiply the top and bottom of that one by 3. So I've really got negative 8/3 plus 12/3. Negative 8 plus 12 would be a positive 4. And then again, the denominator was a 3, so it would stay that. So I've got this tangent line of y equaling 4/3 x plus 4/3 that would be what goes through that point 2, 4, but is still tangent to the graph of this cube root function. All right, let's go ahead and keep plugging away with a few more examples, just so you can have as many options as possible to see how to do these. This first one here, if I were to just rewrite this, this would be the same as doing y equals 4 times 2x plus 1 to a negative 1 power. And so if I go through and just do the general power rule for this, -1 would multiply with the 4 in front to turn into -4. My base of 2x plus 1 remains unchanged, but the power drops by 1, so that would turn into -2. And now times the derivative of the inside function, which the derivative of 2x plus 1 is just 2. So if I simplify, I've got a -4 times a 2 at the end to give me -8. And then I still have that negative exponent, so actually I'll go ahead and set this up because this is going to be a fraction. -8 would be in the numerator, and then the 2x plus 1 being raised to a positive power of 2 once I move it to the bottom would now be my derivative for that function. If we do a similar kind of setup or start to the next example, I'll just rewrite that power on the bottom using a negative exponent. Again, now I can go ahead and try the general power rule. -3 times 2 in front would be a -6. My base of x minus 3 remains unchanged, but my power will drop by 1, so that would be -4. And then times the derivative of the inside function. What's kind of nice with this one is the derivative of x minus 3 is just a 1, so that's not going to change any other numbers. So I do have a negative exponent, so there will be something on the bottom. In this case, the x minus 3 to the power of positive 4 now. And then that -6 would just stay on top because -6 times 1 does not change. So again, just a couple more examples, just dealing with these type of rational functions without having to use like a quotient rule, because after all, the top was a constant anyway. But I did have more than just a simple expression in the denominator. So potentially you've noticed with all of the examples that we've worked through that oftentimes the tough part is the how to simplify the derivative for its final result. So the next two examples I'm going to work through are just going to be a few things to kind of demonstrate some of the possible strategies or techniques to actually go through and maybe use that might make the simplifying process a little easier. So this first one is going to involve the concept of being able to factor out things that they have in common once I go ahead and do whatever the derivative is. So with this one, notice my derivative, or my function really, is a product rule because I have x squared that's multiplying with this square root function. But then you also notice with the square root function that I actually have a function inside of that square root function. So that part's going to actually involve a chain rule. So first thing is always best if you see radicals to go ahead and rewrite using rational exponents. So this really is x squared times 1 minus x squared to a 1/2 power. And then we'll go ahead and now use the power rule, or sorry, the product rule, and then do the chain rule that will use a power rule to be able to evaluate it. So I'm going to go ahead and keep x squared, then multiply by the derivative of the square root part, so that would be where 1/2 would come out front. My base of 1 minus x squared would stay the same. The power would drop by 1, so 1/2 take away 1, that would turn into -1/2. And then times the derivative of the inside function, which should just turn into a -2x. Then the second half of product rule is to keep the second function the same, but then do the derivative of the first. So I'm going to go ahead and just do the derivative of the first because x squared is pretty easy to do. That would just be 2x, and then times the original second function. So 1 minus x squared to a 1/2 power. So notice product rule created these two terms. It looks like there is a little simplifying I can do, at least with the first one, of the 1/2 and the -2 should be able to cancel out. And so if I look at maybe what each term has in common, notice this is all one term here, this is all a second term here because it's got this plus sign separating them. But it looks to me like the things, if I look at all the parts of them that they have in common, they at least have an x in common. And then they also have this 1 minus x squared in a parenthesis in common. So what we can do is go ahead and factor those two things out. And remember, with negative exponents, we actually want to take out the negative exponent, which then means the other power is really going to look like it actually grows. So this 1/2 that's right here is actually going to subtract by -1/2, so it's really going to add a half to it, or turn into one whole. Now if I write what's left Now that I've factored those two things out of each term, it looks like the first term should have an x squared as well as a negative sign. And I've taken, again, that entire parenthesis here out, and I've taken this x out, and that 2 cancel with the 1/2, so that really is just negative x squared. The second one, I still have the 2, it looks like, and then that power on that parenthesis, remember we're factoring out a negative 1/2, which I forgot to write, that negative 1/2, my apologies. So that did have a negative 1/2 power on it out front, which then makes this one grow by 1/2 to turn into really a power of 1. So now if I were to simplify the inside of that parenthesis, I guess the outside, I could go ahead and deal with the negative exponent and say that that's really an x over a 1 minus x squared to a positive 1/2 power now, or I could even rewrite that using a radical. And then that's multiplying with, if I were to distribute the 2 through, it looks like I've got negative x squared and another negative 2x squared for a total of negative 3x squared. And then a plus 2 or a positive 2. So again, all together in the end, I could rewrite this in the numerator as it's x times the negative 3x squared plus 2. Then all over the square root if you wanted to write it that way, or you can leave it as a rational exponent, 1 over or 1 minus x squared to a positive 1/2 power at this point. It's always good strategy to look at your final result, especially when you get these rational functions in the end, and just see if anything else could reduce, but with this one, nothing on top and bottom matches, so that really is the most simplified version we have. We'll go ahead and do one more example. This one's going to now have a quotient rule involved along with the chain rule, because notice the inside is a quotient function or a rational function, and then I have this power of 2 that's outside. So this one I don't really need to necessarily rewrite since it's already kind of in a nice format, but I can go ahead and do the chain rule part. So the power of 2 would move out front. My base of 2x plus 1 over x squared plus 3 will stay the same. And then that power of 2 does decrease by 1, so that would just turn into a power of 1. And now it's on to the fun part, the times the derivative of the inside. So again, this is the quotient rule. So it'd be low d high, so x squared plus 3, times, in this case, the derivative of the top, which is 2, minus the high d low, so 2x plus 1, times the derivative of the bottom. Well, x squared plus 3, its derivative would be 2x. Then all over x squared plus 3 quantity squared. So now let's look at what we have and see if there's anything that we can combine. It looks like right now we have the numerator of that longer part, the quotient rule part, that maybe I would want to distribute the 2 through. And I could distribute the 2x through this other one as well as the negative at the same time. And so if I go ahead and maybe start splitting up what would be in my numerator as well as in my denominator, it looks like my numerator is going to have 2x plus 1 to a power of 1 from right here. And then I have the 2x squared plus 6, and then a negative 2x squared. Oh, nope, that would be negative 2 times 2, so negative 4x squared. And then a negative 2x times a 1, that would be a negative 2x. On the bottom, it looks like I've got this x squared plus 1 to a power of 1 times an x squared plus 3 to a power of 2. So if I have x squared plus 3 to a power of 1 times another x squared plus 3 to a power of 2, that really would just become an x squared plus 3 to a power of 3. So notice I was able to take those two denominators. Since they actually matched in the parentheses, I was able to just add the exponents or use that exponent rule. Now it looks like I do have a couple of like terms that I could combine in the numerator. I'm going to go ahead and just keep the 2 and the 2x plus 1 in that factored form. And then on the inside it looks like 2x squared minus 4x squared, that would be really negative 2x squared. Then minus 2x and a positive 6. All over the x squared plus 3 quantity cubed. Now if we look at that parenthesis right here, notice I could technically take a -2 out of that, and that would get rid of a couple of negative signs, and it also would make those numbers a little bit smaller. So if I go ahead and take that -2 out of those, that should be able to multiply with the 2 in front, so that would turn that into a -4. Then I've got my 2x plus 1. And then the parenthesis now would have positive x squared, a positive x, and then a -3 if you take -2 out of all three of those terms. And then the bottom just remains that x squared plus 3, quantity cubed. And if you were able to factor that quadratic, that x squared plus x minus 3, any further, it might not be a bad idea, but with this one that doesn't really factor any further. So that would be my y prime for this one. So moral of the story with these is when you have that quotient rule, kind of the thing that you can take advantage of, as you can see here, is when you have your denominators the same, you can then combine it and make it just a single denominator, so it kind of cleans up that fraction a little bit. So anyway, hopefully this video has been helpful for the chain rule. I know I did multiple examples, so hopefully my going through of all of those is something that you found useful. But as always, if you have questions from your homework assignment, just let me know, and I'll do everything in my power to make it make sense. Appreciate you taking the time watching the video, and we'll catch you next time.